Yes. Now let us discuss about spectrum. First of all, what is spectrum? You know, when a white light ray that is produced from sunlight or from an electric bulb is passed through a prism. So this is white light ray. Coming from sunlight or, of course, electric bulb, whatever. You know, this white light ray, when passed through a prism, splits into 7 colors of different wavelengths. Okay. See, this splitting of white light ray into 7 colors of different wavelengths is what we call dispersion. Okay. Now, when this dispersed light is allowed to fall on a photographic plate, okay. Now, this dispersed light is allowed to fall on a photographic plate. You know, these lines spread side by side without any gap between them. Okay. They spread side by side on the photographic plate without any gap. At the same time, they do not merge. They do not mix up with each other. Okay. Means without any gap, but at the same time, they do not merge with each other. One color slowly fades into the other. You all know that they are VGR, right? VIBGYOR. So you can show them this way also. Now this pattern or the impression that is produced on photographic plate is called a spectrum. Now this is what I call spectrum. What do you mean by a spectrum? You know, it is an impression produced on photographic plate. When a white light ray that is coming from either sunlight or electric bulb is passed through a prism, and the dispersed light is allowed to fall on a photographic plate. So simply speaking, spectrum is an impression produced on photographic plate. Right. Now, you know, the thing that you have recorded is a spectrum. And the study about the spectra is plural, spectrum is singular. The branch which deals with the study of spectra is called spectroscopy. Right. Next. You know the apparatus used to record a spectrum is known as spectrometer. In fact, this whole thing is kept in an apparatus. That is what is, of course, called spectrometer. Okay. Now let us see what are the different types of spectra that can be recorded. You know, spectra, or let me say spectrum, is broadly classified into two types: emission spectrum, and the other one is absorption spectrum. Then this emission spectrum is further classified into continuous and the discontinuous spectrum. Now this discontinuous spectrum is again classified into line spectrum and, of course, band spectrum. Line and band. Okay. Now let us discuss about all these things one after the other. Okay. First of all, what is emission spectrum? You know, when a gas is heated, or say subjected to electric discharge, when a gas is heated or subjected to electric discharge, by taking the gas in a discharge tube. I told you what a discharge tube is when we discussed about the discovery of electron. By taking it in a discharge tube, by taking the gas in the discharge tube, if it is subjected to electric discharge, or simply when the gas is heated. When heat energy is supplied or electrical energy is supplied. See what happens. You know, the electrons present in the atoms of the gas, they get excited to higher energy levels. I told you that in general there will be atoms in the gas, in the gases. Now these atoms consist of electrons revolving in different orbits. Now when a gas is heated, electrons present in the atoms of the gas get excited to higher energy levels. So I call this process as excitation. Now when they get excited, by absorbing energy, in the form of photons, of course they are said to be excited, or the process is called excitation. Now remember, in excited state, they are highly unstable. Of course, they got excited, but in excited state, they are unstable. Because they are unstable, being with a higher energy, they just get a de-excite. I mean, they come back to ground state. Okay. In excited state, they are unstable. So within 10 power minus 8 to 10 power minus 9 seconds, they get de-excited. I mean, they return to ground state. See, during excitation, they have absorbed. Now, during de-excitation, they have to emit, right? They'll have different energies in different orbits. In ground state, they'll have some amount of energy. And in excited state, of course, they'll have some other amount of energy. Anyway, that will be more. That is the reason why we call them higher energy levels. So when they are excited by absorbing energy, they go into higher energy levels. And when they return to ground state, obviously they have to emit energy in order to cope up with the energy of the ground state, they have to emit energy. So during excitation, energy is absorbed in the form of photon. During de-excitation, energy is emitted in the form of photon. Everything happens in the form of photon. Right? Now, see this emitted radiation. These are analyzed using spectrometer, as I said earlier, of how to record a spectrum. Yes, these radiations are again passed through a prism, and the dispersed radiations are allowed to fall on a photographic plate. Yes, even here also we do the same. Now, when the dispersed or the emitted radiations are analyzed using a spectrometer, we can actually see bright light on a photographic plate having the dark background. Right? Very interesting. We say bright lines because something is being emitted. And to see bright lines, you cannot see them on a bright photographic plate. You have to use a photographic plate which is dark. So this is very important. In emission spectrum, bright lines can be seen on a photographic plate having dark background. It is observed when heat energy is supplied or electrical energy is supplied. Now, we have analyzed the emitted radiation. Okay. So this emission spectrum is divided into two types. Is of two types. The first one is continuous spectrum. Yes, the best example is what we have already seen. WebGR is the best example. I told you very clearly that there won't be any gap between any two colors. And at the same time, they do not merge with each other. One color slowly fades into the other. Initially, it will be dark. Slowly, it fades. I can show you this way. It will be like slowly it fades into the other. Of course, it becomes little of this type. Initially, it is dark. Slowly fades into the other, and immediately another color starts. Okay, that's it. There won't be any gap. At the same time, they do not mix up. This way. So this is a continuous spectrum. Now coming to discontinuous spectrum. Within discontinuous spectrum, as the name itself indicates, in continuous, there will be no gap between lines. I mean, between the spectral lines. Whereas discontinuous, as the name suggests, lines or bands with the gaps that can be seen. In discontinuous spectrum. Now, as I said, discontinuous is again classified into two types. One is a line spectrum, the other one is band spectrum. Line spectrum consists of lines, bright lines with dark areas in between. Of course, here I cannot show you dark areas, but you can see the lines with the gaps in between, right? This line spectrum is given by atoms. So line spectrum is also known as atomic spectrum. And remember, line spectrum is like fingerprints for elements. It is because just like the fingerprints of no two individuals match, even the line spectra do not match. Line spectra are different for a different element. Line spectrum is a specific Specific in the sense special or different for different elements. Okay. So it is like fingerprints for elements. You know, helium was discovered. Let me give this example. In sun's chromosphere. Based on its spectrum. You know, scientists in fact recorded the spectrum of helium and they found it to be very much different from the spectra that were available at that time. It didn't match with any other spectra. So they thought that it is of a new element, and to that new element, scientists gave the name helium because, you know, helios is a word which has the meaning sun. Helios is nothing but sun. It was discovered in sun's chromosphere on a complete solar eclipse day by Johnson and Lockyer, two scientists. So this is all about line spectrum. You got gaps between the lines. Of course, the bright line. Now, coming to band spectrum, just like atoms combine to form molecules, you know, let me take a different color. Just like atoms combine to form molecules, even lines combine to form bands. This way. Of course, a band spectrum consists of bright bands with dark areas in between. See, these are called bands. Of course, these are lines, right? Now, the bands are separated. There is a gap between the bands. Remember, band spectrum is given by molecules. So, it is also known as molecular spectrum. Very interesting. Line spectrum is a characteristic spectrum of atoms. So, it is also known as atomic spectrum. You know, the band spectrum is given by molecules, or it is a characteristic spectrum of molecules. So we call that a molecular spectrum. Okay. Now, let us just go for emission spectrum. For the absorption spectrum, anyway, we have done with emission spectrum. Come on. What is absorption spectrum? Yes. Now you have to be little more careful. Some amount of a gas is taken. You know, light is passed through the gas. When light having different wavelengths, when passed through the gas, you know, here we'll be analyzing the transmitted radiation. This is called transmitted light. Now, this is what we are analyzing. This is what we are going to analyze. This is analyzed using spectrometer. Remember, you are not analyzing the absorbed radiation. You cannot, in fact, can you analyze the thing that is already been absorbed by the electrons present in the gas? No, you cannot, because electrons present in the atoms of the gas, they just absorb and they just get excited to higher energy levels. Now you cannot analyze this portion, but indirectly this can be known by analyzing the transmitted light, because hope you all can imagine. See, you have sent a light having a different wavelength. Some of the wavelengths or some of the radiations having particular wavelengths have been absorbed by the electron. Now they'll be missing in this, isn't it? Absorbed radiations will be missing. Suppose, let us say that you got X angstroms, Y angstroms, Z angstroms, W angstroms kind of radiation. Now, supposing if X angstroms wavelength and Z angstroms wavelength have been absorbed by the electron, will they be present in the transmitted light? No, no. Then what are the wavelengths that will be there in the transmitted light? Yes, only the Y1 and the W1. Y angstroms and W angstroms will be there in the transmitted light. So what do you say? Because Y and W have come out in the transmitted light, of course, this all can be known using a spectrometer. Because Y and W have come out, what we can say is X and Z must have been absorbed by the electron. So what are the wavelengths of the absorbed radiation? X and Z. What have not been absorbed? Y and W. So in the transmitted light, you know that the portion of the radiation, what is being absorbed by the electrons will be missing. Because X and Z are missing in the transmitted light because they have been absorbed by the electrons, and only Y and W are available. When you analyze the transmitted light, you know, you can see some dark areas because X and Z have been absorbed. Now they are missing. In those missing areas, you can see dark areas or dark lines. Now these dark lines, of course, can be seen on a photographic plate having a bright background. Yes, of course, to see the dark lines, you need to use a bright photographic plate. See, here you got dark lines. To see them, you have used a bright photographic plate. Whereas in emission spectrum, we got some bright lines on a photographic plate having dark background. And remember, one very interesting thing is bright lines in emission spectrum and dark lines in absorption spectrum both are formed at the same position or same place, because you know these two have the same wavelength. I told you very clearly that, yes, whatever wavelength that is being absorbed during excitation, you know, the same wavelength of radiation will be emitted during the excitation. So the absorbed one and the emitted one obviously must have the same wavelength. So that is the reason why when you analyze the emitted radiations, you get bright lines. And you know, when you analyze, of course, you cannot analyze the absorbed one. You can only analyze the transmitted one. I told you no, because they have already been absorbed and the electrons have just gone up to higher energy levels. But only thing what we can do is that has come out of the gas, nothing but a transmitted light. This is analyzed for recording absorption spectrum. But of course, we are not talking about the radiations or the wavelengths that are available. We are talking about the wavelengths that are missing. That is where we get dark light. Why are they missing? Because they have already been absorbed. So they'll not be there in the transmitted light. That is the reason why you got dark light in those areas. So absorbed and emitted radiations will have the same wavelength. That is the reason why you get bright lines and dark lines at the same position or at the same place in the spectra, because absorbed and emitted radiation will always have the same wavelength. Yes, of course. If suppose you require some amount of energy or some wavelength radiation in order to get excited to this level, and again while returning to ground state, obviously you will be emitting the same amount of energy or same radiation of the same wavelength. Because from here to here, if the difference is say x, x is being absorbed, then from here again, when it gets back, when it gets de-excited, the same x amount of energy is emitted. X is absorbed, x is emitted, right? So they'll have the same wavelength or they'll have the same energy. That's it. That is the reason why you get dark lines and bright lines at the same place, same position, indicating that they are of the same wavelength. This is about absorption spectrum. Now let us go for the very important one, that is hydrogen spectrum. Now let us check. You know, when hydrogen gas is heated or is subjected to electric discharge, of course you get the emission spectrum of hydrogen. I told you that heat energy or electrical energy are used for recording emission spectrum. Now otherwise, light is focused on the gas and the transmitted radiation is analyzed, right? This is what we do if we want to go for absorption spectrum. Take any of these. Either you go with the emission spectrum or go with the absorption spectrum. Of course, you see bright lines in emission spectrum on a dark photographic plate, and in absorption spectrum of hydrogen, you can see dark lines on the photographic plate having bright background. Whatever may be the type of lines, but of course they belong to the same wavelength, right? Now, in the spectrum of hydrogen, we'll have a different lines. Number of lines can be seen in the spectrum of hydrogen. It is because when hydrogen gas is heated or subjected to electric discharge, or when light is passed, what happens? Electrons present in the atoms of the gas get excited. Yes, we know that. Now in this I have two cases. Let me tell you that if the energy supplied or if the energy absorbed by the electrons is greater than or equal to, say, 13.58 or 13.6 electron volts, this is the ionization energy of electron. I mean the energy required to remove the electron completely from the atom. Now, if suppose electrons absorb energy equal to or greater than this, then obviously the electron just goes out because you have given its ionization energy. Then what do you get? Yes, if the energy supplied is greater than or equal to 13.6, electron is completely removed from the atom. I mean, it goes out of the atom, and then atom is said to be ionized. Then you get H plus. Electron is completely removed. That is the reason why you got a positive charge, isn't it? H plus ion is formed. This, of course, is case 1. But what if the energy supplied is less than 13.6 electron volts? Of course, the electron cannot just go out of the atom because you have not given its ionization energy, because you have not given the energy that is sufficient enough to go out of the atom. It will remain in the atom. Let me tell you what happens. Coming to case 2. If the energy given or supplied is less than 13.6 electron volts, then electrons get excited to one of the higher energy levels. What I mean to say is, remains in the atom itself, doesn't go out. Now it simply got excited to higher energy levels. Now, as I said, in higher energy levels, it is unstable. Yes, of course. I told you many a times that any system with a higher energy is less stable, as energy and stability are inversely proportional. See, because it is unstable, within 10 power minus 8, to 10 power minus 9 seconds of short period, gets de-excited to ground state. Yes, of course, you cannot be in excited state. You cannot be angry for longer period. You have to just calm down. You have to just cool down, right? Just like we human beings get angry over things, but this remains for a shorter duration. Of course, we cool down or we calm down and we become normal. The same way, even the electrons, of course, they get excited when energy is given to them in the form of photon. But in higher energy levels, they are highly unstable. So they simply get de-excited to ground state. But here again, there are two cases. Of course, every single electron reaches ground state. But some reach directly from the higher energy level that they got excited directly, or some other, of course, reach ground state again, but indirectly through stages. So these are the two cases. See, if the energy given is greater than or equal to 13.6, the electron will no longer remain in the atom. It just goes out of the atom, giving you H plus. But if the energy supplied is less than 13.6, I mean less than the ionization energy of the ionization energy of electron in hydrogen atom, no doubt it cannot go out because the energy that is supplied is less than what is required. So it remains in the atom. Of course, remains in the atom, but anyway, it got energy, so gets excited to one of the higher energy levels. Remember, infinite number of orbits are possible. There may not be electrons in the orbits, but you will have orbits, not just one, because hydrogen has 1s1 configuration. Don't think that it will have just one orbit. No, it will have infinite number of orbits. The point is, electron is just one. Only one electron is there in that, and it will just revolve in the first orbit. But there will be orbits, though there are no electrons. So when there are infinite energy levels are possible. Of course, electrons get excited to say fifth, the sixth, the seventh, the eighth, the ninth, or 10th, like that, of any of these orbits. But in those orbits, it is unstable. So it has to get de-excited to ground state. But within that also there are again, suppose there is an electron in say fifth energy level, I mean fifth orbit. It may just return to ground state straight away. Like suppose fifth to first. Let me give this example. I mean just only one transition, isn't it? Because this is only one transition, I mean it is straight away coming down to first. In the spectrum, you can see just one line. Only one line can be seen in the spectrum. Now, when you go for, the same fifth orbit electron, if the electron in the fifth orbit, it gets de-excited to ground state, there are several other possibilities. It may come down in steps like fifth to fourth, it can go. Then from fourth to third, from third to second, and then from second to first. Anyway, it reaches ground state. In this process, you get 1, 2, 3, 4 lines corresponding to 4 different transitions. May not be this. It can even be this also, fifth to say fourth. From fourth, it can directly go to first. Different possibilities. In this case, you get only 2 lines. Right? In this case, you get 5 lines. In this case, of course, you get 2 lines. It may even be like this also. Say fifth to third, third to first. Even in this case also, you get only two lines. It can be like fifth to fourth, fourth to second, then second to first. You get three lines. So that's how there are different possibilities. When you say indirectly through stages, you will have different possibilities. But only thing to be noted is, when you go down, when the electron goes down or gets de-excited directly to ground state, you get just one line. Whereas when it goes indirectly, then you get more than one line. So that is, of course, very interesting. And now all these lines, because every line corresponds to a radiation. Of course, when it goes down from fifth orbit to first orbit, energy is emitted, and that belongs to a particular wavelength. When that radiation belongs to a particular wavelength, it will sure belong to one of the regions of the electromagnetic radiation. It may belong to UV, it may belong to visible, it may belong to IR, it may belong to some other. Okay. Even here also, if suppose you are getting 5 lines, the 5 lines belong to different regions. So depending on the region in which they are formed, the lines are classified into different series. Okay. See, the spectral lines formed are grouped into different series. See, you got different lines. One line in some cases, many lines in some other case. Now all the lines, based on the wavelength of the radiation, they are grouped into different series. Nothing but based on the region in which they are formed. When I say region, it is like UV or visible or IR. You can also say based on the wavelength, not just wavelength. When you say wavelength, based on energy, based on frequency, based on wave number, it can be anything. But they are grouped into different series. I've got 6 such a series. Let me tell you what they are. See, the first one is Lyman series. I'll just give you the names. We have a great discussion about all these. Then the second one is, of course, Balmer series. In fact, Balmer series was the one that was discovered first by the scientists because it was found in visible region, the only region which could be seen with naked eye in those days. Of course, even now, visible can be seen with naked eye. But the other regions of the electromagnetic radiations cannot be seen with naked eye. You need special apparatus to see them. Lyman, Balmer, Paschen. Then the fourth one is Bracket. Then the fifth one is Fund series. Fund, P silent. And finally, there is something called Humphrey series. So these are the 6 series that were classified on the basis of the region in which the different spectral lines are formed. Okay, Lyman, Balmer, Paschen, Brackett, Fund, and finally Humphrey. Okay. Then, how are these series formed? I mean, when are these series formed is the next discussion.